Vishwas, please.
Sure, ma'am. Thank you. So today our instructor will be Mr. Shivang Trivedi. Mr. Shivang is an entrepreneur and an AI consultant. He has his experience in deep learning, algorithm design, and software project management. He has founded multiple companies in AI space, namely M. Einstein, LLC, Condensius Technologies Private Limited, and CTL Indoor. Okay, currently he's working with a very senior. Working with very senior people in the industry. He has successfully designed, developed, and deployed complex AI solutions in various industries like healthcare, logistics, and retail. Shivang is a graduate of Indian Institute of Technology, Roorkee, and has keen interest in teaching AI to people. So we are glad to have you as an instructor today. You can take up the mic.
Thank you. Am I audible? Am I audible?
Yes, sir. Yes, sir. Yes,
Is
sir.
there any kind of a noise from behind? Is there any kind of a noise?
No, but your voice is little low.
Okay. Is it better now?
Yes, sir.
Okay. Let me share my screen. Just give me 1 second. So how many people do we have today?
Sir,
How many people do we have today?
sir, actually, it's a YouTube link.
Okay.
Nearly 1.5K students will be joining every day.
Okay.
So all these people are watching us, sir.
Okay. So, hello everyone. Good morning. This is Shivang Trivedi. Nice to meet you all. We will be discussing on the topic of data structures and algorithm design for next 5 classes. We'll try to teach you algo. Just give me 1 second. Let me share something in front of you. 1 second. So much noise. Just 1 second, guys. So, here we are. I am now sharing screen to you. So that you will be able to see this. Okay, can you see my screen? Yes, you can. Okay. So hi.
Yes, sir. Yes.
So let us start programming. And today's topic is data structures and algorithm design. What is data structures and what is algorithm design? So what is algorithm? Basically, a step of instructions that a computer can follow. And by following those steps of instructions one after one, we want our computer to run the program and solve the problem that we wish to solve. That is what we want. We want to build softwares so that we can develop technology, and the building block of a software is a program. Every program in some way is a set of instruction. That set of instruction in some way is nothing but an algorithm. If you can create a right algorithm for a problem, your computer will be able to solve it and run that algorithm again and again, maybe for a million number of time without any failure. By data structures, we understand. So we understand we have an algorithm. The course, we will be going through some algorithms like search algorithms. How can we search a database? Google is a search engine. It is also searching something. There are different search algorithms that we can do. We'll also be looking some tasks like sorting. Oops. So sorting algorithms are also something. Arranging something in a increasing or a decreasing order. So instead of getting into the commercial aspect of why we want to search things or why we want to sort things, we will only consider them as these two tasks, and we want to develop a program which can do this task. And that is what our objective will be, to design an algorithm which can perform these two tasks: search some data, sort, arrange some data. Now, while our program is doing that thing, it will take some time to solve that task. It will also take some memory to solve that task. For example, if I say I divide 15 by 4, what is my quotient? This is a problem that I want to solve. For example, now there are two numbers, 4 and 15. I know that I need to multiply 4 by 3. This is going to give me 12. And my remainder is going to be 3. Now, to find the remainder, if my problem is what is the remainder if I divide 15 by 4, I need to store some numbers. What are these numbers? Quotient. One is a quotient, which is 3. I also need a divisor, small d, which is 4, which is going to divide the number. I also need a number that needs to be divided, which is 15. And then only I'll get my remainder, which is my answer, which is 3. So to actually get the answer, I somehow need to remember all these 4 numbers, 15, 4, 3, and 3. So I need some memory to do this task. I do something, or somebody else do something, computer do something, or any other machine do something. Algorithm is a set of instructions. So I can also follow a set of instructions to arrange a deck of cards. If I have like 52 deck of cards, and I want to arrange them in an increasing order or decreasing order, I can follow some tasks to some steps to do so. Not necessarily algorithm is something that can only be used by a computer. If you have seen a Rubik's Cube, the 3x3 Rubik's Cube is something that you can move in some way to arrange it. And if you have tried to solve that entire 3x3 Rubik's Cube, you will find out that it is sometimes difficult to do so because you don't know the exact mechanism. But if somebody tell you the step-by-step procedure to do so, or if you by yourself find out the step-by-step procedure to solve a Rubik's Cube, you will always be able to follow those steps and solve the Rubik's Cube exactly. You don't need to actually derive that, even if you can follow that. If I tell you, then you will also be able to solve a Rubik's Cube. The same thing is for everything else. if there is a problem and if somebody can tell you a step-by-step way to do it, that is an algorithm. More conventionally, step-by-step instructions that a computer can follow. Now, if there is an algorithm, it is going to take some time to solve, and it is going to take some space, memory to solve. Time and space both are very important resources for us. We want such algorithms that can solve problems faster. We don't want to create the algorithm that takes 30 years to give you an answer. We also don't want an algorithm that takes 50,000 terabyte of memory to solve a problem. So resource, which is time and space, is something, and we want to derive faster algorithms. Now, the way you can derive faster algorithm is if your data is arranged in a particular way, or if you look your problem into a particular structure of data. We will very soon see this thing, while we will see something called a linear search and something called a binary search. And we will see that the algorithm which is binary search, which is the topic of today, the linear search and binary search, we will see that the binary search is very fast as compared to linear search. How fast it is, that is a question we will see. But you will figure out that you cannot run binary search on any data. You need to have some kind of an arrangement. This is a very crude example of illustration of what I'm trying to say. But you will figure out that there are certain algorithms which are faster, but requires a certain kind of arrangement or a structure of data to be performed upon. That's why the two terms, algorithm design and data structures, are highly connected to each other. Yeah. Okay, so consider something called an ARR, array, whatever be. It is a list of numbers. I put any given numbers.
So sorry for disturbing you.
Yeah.
Actually,
Yeah.
the voice is not clear.
Huh.
And also there is some disturbance in the background.
I understand. Is the voice clear now?
Your voice is clear, but it's in between it's breaking, and also from the outside surrounding we have some disturbance.
I, at least for today's class, cannot handle the disturbance. I'll try to get the disturbance as low as possible, but that is an issue. Just 1 second. Just 1 second.
Okay.
Yeah. So I can't help the disturbance today because I'm in this place where there is a lot of disturbance. Can we cope for today?
Okay, sir. Okay.
My apologies for this. I am in a small place right now and try to arrange a system to get this done. We'll ensure some kind of a solution for this ahead. Now, I'll try to speak as loud as possible. Where we were, we have these numbers in front of us. We have something called array, which is a list of numbers in front of us. And our goal is to find out the position of the number. So for example, we say that number 1 is at 0th position. This is at 1st position. This is at 2nd. This is at 3rd position. This is at 4th position. This is at 5th position. 5th position right now. And this is going to be on 6th position. Now, I want to create an algorithm or a program. If I give an input, of 100, it should give an output of 5. Which 100 is at 5th position. If I give an input of 3, it should give me an output of 1. Because 3 is on first position. If I give an input of 1000, it should give an output of -1 because 1000 is not present in this list. So this is our objective, and we want to create an algorithm or a program that can generate such results to us. Okay, how can we tackle this problem? That is something called a linear search. And how can we tackle this problem? So what we can do right now is we can run something called a loop. If I start from index 0, so let's start from index 0, and every time, so start from index 0, which is going to be my index is equals to 0. Now, let's suppose that what is written on this index is area of index. So area of 0 is going to be 3, and area of 1 is going to be, area of 0 is going to be 1, and area of 1 is going to be 3, and area of 2 is going to be 5. Let us suppose this is how the indexing of my array is going to be. Now, what I can do is I need to search my number, my input. Let's suppose my input is 100. What I can do is I can compare starting from 0 to the length of the array, see one number at a time. So currently my length of the array is 7, 0 to 6. And if I do so, at every step, I can compare whether my number is equal to the current number in the array, if that is the thing. So for example, what I'm saying is, let's suppose for I starting from, or index starting from 0 to 7 in this case, or length of the array in any general case. Let's say length of the array in any case. For now, let me write this will be n. So I'm starting from 0 to 1. Every time my index is going to increase. So if I print my index here, what should this do is start printing number 0, then 1, then 2, then 3, then 4, then 5, then 6, and so on. So start from 0, reach to 6. And if I print area of index, and it should be printing all these numbers 1, 3, 5, 12, 45, 135. So I can iterate over this list. And if I iterate over this list, I can also compare with my input, which is 100 right now. And I can say if at any given point area of index, or now instead of writing this entire index, I'll simply say I, which basically means index. So if array of I is equals to, I'm comparing this with input. If this condition is true, what I can do, don't get into syntax of this for the concept. If this is the case, I can print the index itself. So for example, right now I is going to be 0. So 1 is not is equals to 100. Then next iteration 3 is not is equals to 100. Next iteration 5, 45, nothing. And at this point, when I is equals to 5, array of I is equals to 100, I can print this and I can simply break the program. I'm considering you understand the basics of programming at this stage. And once you do so, that's it. You get the answer, you get the position of the number from where the element is. And if you run the entire loop, so if you run the entire loop and you don't run this condition at any given point in time, your I is going to be n. So with this condition, you will figure out that there was no element in the entire array which was equal to the input. So for example, the case of 1000. In this case, you will figure out that I is going to be 7. By following the general for loop, you will see iterate the entire for loop and you will not find this anywhere. In case of 100, you could see that it is 5 because at the 5 position, you are going to break the loop, and in 1000, you are not able to break the loop. If that situation happened, you can simply print -1. A simple working example of linear search or view return or whatever you want to do. So basically, you are starting from left to right, you are iterating every number into a list, and wherever you find it, you simply print the index or you do whatever you want, work around and do any other activity other than printing. You can't figure out it anywhere, then you say that it is not available. So the question is, how much amount of time it is going to take to solve this problem? Now, instead of considering time in measuring it in terms of seconds, because one computer can run it faster, another computer can run it slower, let us see time as number of operations required to solve this problem. So let us see how much operations will be required to solve this problem. Now, if I say I is equals to 100, then on the first number itself, we will match the number. We'll say that, okay, the first element is there. We'll print and simply get it done. If my number was on the first stage, the number of iterations is relatively very low. But if my number was 34, if it was on the last, or if it was not at all there, then I need to traverse the entire array to actually get the answer. So at this stage, I can say that the total number of steps required to get the answer is proportional to the size of the problem. As this n increases, number of steps also increases. So if n is 1 million, you need to perform 1 million operations. If n is 1 million, for example, let's suppose n is equals to 1 million, and your computer can do 1000 operations per second, then you will require almost 1000 seconds to solve this problem. 1000 seconds is how much? Almost 15 minutes. And if n was 100 or 1000, then you can solve this problem in 1 second. So as the size of the problem, which is the length of the list, the bigger the list, more time you will require to solve the problem. In the worst case, best case is always right. If this is a 1 million length list or a 50 million length list, if my number is always on the first place, it is going to be constant. It doesn't matter how long my list is because my element is always on the first place. But when I see the worst case situation, I'll figure out that in worst case, the length of the array as increases, the time to solve the problem also increases. Even when we do the calculation, we include some probability, we will also be able to find out that on average case too, it is big of array. So if you quickly get into the average case of a linear search, so your number can be at any position. So for example, if there are n numbers, so we say that best case, the time is order of 1 constant. Worst case, the time is order of n. As increases, time to solve the problem also increases. we want to find out the average case. Now, my number can be anywhere. So if there are n numbers, if are n numbers, probability that my number will be on first position or at any position is 1 by n. So if I have like two numbers, 50% first position, 50% second position. If I have 100, 50%, 1 by 100, 1 by 101 to be very precise, but one possibility is not there. But basically, the probability is anywhere. So what is the probability? What is the chance that like how many operations I need to do depends on whether it is on first position or second position or third position or fourth position or so on. So if it is on first position, I need to do one operations. If it is on second position, I need to do two operations. If it is on third position, I need to do three operations. And on general, I can sum this up. 1 plus 2 plus 3 plus so on. And this is going to be, if you do the math, n into n plus 1 by 2. If this is the size, then at every position it is going to be 1 by n. This is the last time you get the noise, now you won't get it. So the average time to solve this problem is going to be n multiplied by n plus 1 divided by 2 into n. So basically, in average case 2, you will find out that it is order of n. As the problem size increases, your computer will take more time to solve this. If the problem size is really large, it will take more time. Now, instead of this, if I arrange my data into an increasing order, for example, 3, 50, 25, 50, 100, and I will imagine this is the way my numbers are. And this list can be really big, 1000 and so on. If this list is really big, then what I can do now is, let's suppose my input is 15. I need to find out where my number is. Now, because this is a sorted list, because it is like, consider the example of a dictionary. Now, dictionary has a lot of pages, lot of words written on one page, but instead of that, if you have a kind of dictionary where only one word is written on one page, but it is written in a lexicographical order, so the word apple will come first and boy will come second. Instead of that, consider a book where every page of that book is having some number. So first page is having 3, second page is having 15, third page is having 25, fourth page is having 50, fifth is 100, sixth is 500 and so on. If that is the case, and you need to find out a particular word, you don't need to read all the pages in a linear order. Read the first page, second and so on. You can simply open the book from in between. And once you open the book from in between, you will reach out and see, okay, 50 is written on this page. Now, if 50 is written on this page, you are very sure that if 15 is present in the book, it is always present on the left side, because you know that the book is sorted. If I wanted to find out 500, I open the book, I saw 50, I know that the only right side of the book from 100 to 1000 is something that I need to see. And if 500 is over there, it is going to be there itself. So then I break it in half. I reach 15. I get it over here. If my number was 25, then I know that first time I get 50. I know that 25 is going to be on the left side. I again take this part, this much amount of part, break it in half. I will be able to figure out that I reach on 15. And if 25 is there, it will only be on this side. So if my list is sorted, I am doing a binary search. I'm dividing the list into half and half and half, and then trying to get the answer. So if I quickly write this, I can say I have a start, which initially is going to be 0. I have an end, which is going to be n minus 1, length of the array. So length of the array is 1, 2, 3, 4, 5, 6, 7. Last number is going to be at index 6. Now, the midpoint in this case is going to be start plus end divided by 2. And you can have a integer round off of this. So for example, if start is on 1, if start is 1 and is equals to 10, then average is going to be 5.5. But when you only take the integer part, you land on the 5th position. So this is the position that I want to reach. Average position in between. Now, I want to find the input, which in this case is 15. What I need to do, I set start is equals to 0, end is equals to n. Now, if my number array at this position, the element of this position is equals to input. So let us again put all these numbers. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. If this is the case, then my position is going to be 0 plus 6 by 2, which is 3. So I'll reach on the number 50. Now, this condition, if happens, I can simply print position. I found that number, and I can break it. But if this number is not there, then there can be 2 scenarios. Scenario number 1 is the number that I've found is greater than input or smaller than input. So for example, 50 is greater than input. If my number which I've found out, which is the number written on that particular position is 3, area of 3 is 50. If that is greater than my input, which is 15, what I need to do in this particular case, what I need to do is I need to see the left half of the solution. I mean the left half of the list. So left half of the list, I need to update the value of start and end. Now, left half is my start is going to be the start. Definitely, start is not going to change. Start is going to start. Basically, I don't need to write it. My end is going to be position minus 1. Correct. So now I only need to look into this half, 0 to 15, because I hit the entire list. I saw that the middle number is 50. I couldn't find 50. 50 is not the number 50. So I look into the left half, 0 to 2. And now, again, same process needs to be repeated. If basically the another condition, if my number was greater than, then my end is going to be the same. If I was looking for 500, my end was going to be the same, but my start will become position plus 1. And this process will keep on repeating while my start is smaller than end. Once for example, I need to find out number 0 in this list. So my start is going to be 0, end is going to be 6. Now my P position is going to be 0 plus 6 by the 3. Position at 3, where are P is 50, which is not 0. So I need to again look at the half part. In that perspective, my start will be 0. My end is going to be 2. My position is going to be 0 plus 2 by 2, which is 1. An array of 1 is 15. 15, which is also not the number that I want. Again, my start becomes 0. My end becomes 0. 3, which is also not the number. And now, because start and end are equal and still this condition is not satisfied, so I can say smaller than or equal to. Now you can't do anything. You have to break the loop and you have to come out. So this entire thing goes inside this loop. And you will find out that if this program is done repeatedly again and again, we will keep on breaking this into half. We'll break it. Else, I can simply put I want to make sure that if this condition never run, if this flag condition never run, in that case, this condition will not be true. So I can simply do the same trick. If start is greater than end, this condition happens basically, or I can put it else right here. If we try to be technical, I can simply print -1. The number is not present. That's binary search. We'll look into this in more detail because there is a lot of disturbance, so I don't want to extend the class very long. But the point is, this is another approach of finding the same number. Nobody stopped me write the same program for I starting from 0 to n if array of n array of I if array of I is equals to input print I, and if I equals to n print -1. Nobody stops me write this program, which is a linear search. But if my data is arranged in a sorted order, I can actually run this program and solve the same problem in some other approach. But the question is how fast this is going to be. So we need to see this. So if my length of the array is, let's suppose, if n is worst case scenario is, I see the entire list and that number was not present. So how many number I need to check? So length is 64. If I see the number that I need to see is 32. Now I can't find it. Then I break it. 16th page. Consider a book of 64 page. Now, if you do the linear search to find the number which is not there in the book, you need to read 64 pages. And then only you will be able to say that the number is not there. But if all the numbers are in increasing order, then first you are going to see the 32nd page. Then you are going to see the 16th page. Then you are going to see the 8th page. Then you are going to see the 4th page. Then second page, then one page, and you get the answer. You have only read 1, 2, 3, 4, 5. Basically, what is 2 to the power x that makes it 64? That is the question. So, because you are breaking it in half, what is the 2 to the power? You can do it. 16 pages, you break it to 8 or so on. So, what is 2 to the power x, which makes it 64? So the question is, what is log 2 of 64? 64, which is 2, 4, 8, 16, 32, 64, which is 6. very less than 64. So now you only need to read 6 pages if the book is in a sorted order. So for a sorted order list, or for now our example we call it a book, we can say that the total number of operations which is required to do is log base 2 of n. So again, we see our problem. If n was 1 million, our computer was doing 1000 operations per second. If we implement a linear search, then it will require 1000 seconds to get the answer. In the worst case, 15 minutes. On the same computer, if we apply binary search, then the total searches that you need to do is, what is log base 2 of 1 million? So log base 2 of 1 million is 21, something like this. And 21 pages you need to read, 21 operations you need to do, and your computer can do 1000 operations per second. So basically, you need to have 0.021 seconds to get the answer. So same problem, same computer. Linear search took 15 minutes. Binary search took 0.01 millisecond. So that is what two different algorithms solve the same problem, search problem. One is way faster than other. But the only thing is, you cannot run a binary search on an array which is not sorted. So you cannot run it on another array which is like 3, then 1, then 50, then minus 24. You cannot do this. The assumption that binary search was that the array is in a sorted order, it is in an increasing or a decreasing fashion. The data is particularly arranged in a sorted way. Then only you are able to run the binary search. So we see that there are certain assumptions over which binary search was running. Similarly, we have different algorithms like linked lists or stacks and queues and trees and graphs. Different data structures. And we have certain algorithms which runs on a graph data structure, and there are certain algorithms which run on tree data structure. And the reason is, for certain problems, certain kind of algorithms are faster if the data is in a particular data structure. So that's why it is necessary for us to read all the data structures, like some of them we are going to cover in this session. And accordingly, while the data is in a particular data structure, we will be able to leverage certain algorithm design techniques to solve or to create more efficient and faster programs. For example, right here, linear search, order of n, binary search, log base 2 of n, which is far faster than that. Similarly, we can write binary search in a recursive way. But because today we are having a lot of disturbance, I would like to conclude the class today right here, and by tomorrow, I'll make sure that everything is much more streamlined. Thank you. So because we are on a live session thing, so I don't think so we will be able to have any kind of interaction. So I'm stopping the class right here. My sincere apologies for any kind of disturbance that you have seen. But by next class, we'll make sure that everything is fine. And if the students say, we will be able to retake the entire session for tomorrow in a much more detailed way and in a much more calm environment. So if that is something that is a requirement from the student side, we'll make sure that we take another session and discuss everything in much more detail. Thank you very much.
Yeah, dear students, today's session we are ending here because there is a disturbance in the area where the instructor is teaching you. So please, we'll try to divide tomorrow. Okay. Today's session we are ending here. Thank you.